Welcome to Excel 2013 Statistical Analysis video number 69. Hey, if you want to download this Excel workbook file and follow along, or the PDF file, click on the link below the video. Hey, in this video we want to talk about completely randomized design and analysis of variance, or Anova. This is going to be our method for comparing more than two population means. Now, before we define completely randomized design and Anova, let's just look at our example and set it up first. Now, our example, we're going to be a boomerang manufacturer, and we're considering 4 different methods for manufacturing the quad boomerang. There's a little picture of the quad. A random sample of 20 workers. We have 100 workers in our factory, and we're randomly going to select 20. From those workers, the workers are randomly assigned one of 4 manufacturing methods. Each worker is timed making quads with the assigned manufacturing method. Time is recorded in minutes and rounded to 2 decimals. The mean time for each method is recorded. So you could see here method 1, 2, 3, 4. There's the 5 workers for each one of the methods that were randomly selected. Down here we have the mean for each one of those. And those are the 1, 2, 3, 4 means that we're going to try to show that there is no significant difference between these 4 average times, which means there's no significant time difference between the 4 methods, or there is a significant difference between the times between the 4 different methods. So we want to determine if there's a significant difference between the 4 mean times, or we could ask the question, are all the means equal? Now, I'm going to page down and go to our next page. Now, from the sample data, we want to ask this question, is mu sub 1 equal to mu sub 2 equal to mu sub 3 equal to mu sub 4? Remember, those would be the mean times for each one of the methods. We're going to set this up again. The numbering is important. 1, 2, 3, 4. Our point estimate for each one of those population means are here. For method 1, it was 12.73. For method 2, it's 13.83. Method 3, 14.01. And method 4 is 11.31. Now, notice we have 1, 2, 3, 4 samples. We could use the techniques that we've already used in this class. But guess what? If we were to compare each mean one at a time, we'd have to run 6 tests. Remember, from our combinations, 1 would have to be matched up against 2, 1 matched up against 3, 1 matched up against 4, and then 2 against 3, 2 against 4, etc. 6 different tests. And the big problem with that is if we ran 6 tests, we would build up a lot of type 1 error. If our alpha is 0.05, the probability that they're all correct, and this comes from Chapter 4, our multiplying rule, 0.95, 6 times, so the probability that they're all correct would be 0.735. And if we remember our complement rule, if we want at least 1 not correct, that would mean 1 or 2 or 3 or 4 all the way up to all 6. We could take 1 minus that. Wow, that is a huge amount of type 1 buildup risk. So even though we had alpha of 0.5 when we ran all 6 tests, we'd have a huge alpha risk. And also, of course, we'd have to do many calculations to test all 6 means. So we have to learn a different statistical method to test this. And I'm going to page down. Here it is, analysis of variance, Anova. And it is a statistical method to check whether k population means are equal. So we can check however many we need. In our case, we have 4. Now, the strange thing about Anova is that the terms factor, treatment, response variable, and experimental unit, they all come from agriculture. So check this out. Instead of saying independent variable of interest, the manufacturing method for quad boomerangs, we would just call that the factor. Instead of different populations, notice we have method 1. There's a bunch of times there. Method 2, a bunch of times. Each one of these methods has its own population. So there's 1, 2, 3, 4 populations. But check this out. We call it treatment. So instead of population 1, population 2, population 3, etc., we're going to say treatment 1, treatment 2, treatment 3, treatment 4. Not only that, but instead of saying dependent variable, which is our time to make the quads in minutes, we're going to call that the response variable. This is a single factor because we only have one factor, manufacturing method. And then also the term experimental unit means the object of interest in the experiment. For us, it's the people making the quads. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So each one of those is an experimental unit. Now if we go to our next page in our PDFs, page down, and I'm going to use the keyboard Control-Shift+ to turn it on its side. The definition of completely randomized design, an experimental design in which the treatments, remember that's the populations, are randomly assigned to the experimental units. Treatments, populations, the manufacturing methods are randomly assigned to experimental units. That would be the actual worker. So for us, CDR, completely randomized design, means randomly assigning manufacturing methods to workers. Now I want to go over to Excel, and on the sheet CDR2, here's what we did. If I control down arrow, I can see I have exactly 100 employee names. And from earlier in our class, we learned about simple random sampling. And we would randomly select and get a list of 20 workers. Once we have these 20 workers, then we need to randomly assign the method for each worker. So we can see here, Willard is method 1, Jody is method 1, Guy, Van, and Floyd. So 1, 2, 3, 4, 5. Those are the times for Willard, Jody, Guy, Van, and Floyd. All of this was randomly selected so that in the end we have treatment 1 to 4 and our 5 times where we can start to calculate averages, variances, and do our analysis of variance. Now I want to go back over to the PDFs, Control-Shift-, and then page down. Now we need to talk about our assumptions for Anova. The first assumption is the population for the response variable. Remember, that's time to make the quads. Follow a normal distribution. Second, the population variance of the response variable are the same for all populations. And you can sort of see a picture down here. Here's the conceptual overview of Anova. If, in fact, the means are all the same, which means the time, the mean time for making the quad boomerangs for all 4 methods, then it would come from one sampling distribution. And we went out and got our samples. It would just be some close-in sampling error. If, in fact, the means are different, it might look something like this. Each one of the population means would come from a different sampling distribution. Our third assumption for Anova, observations must be independent. That means not related or linked or influenced by other observations. Now, our whole key to this Anova calculation is going to be the analysis of variance. Now, what we're interested in here is the variation. There's lots of variation here, whereas here there isn't any variation in our theoretical perfect situation where all the means are exactly the same. So it's variation. And earlier in the class, we had different measures of variation, and the one we're going to use is variance. Remember, variance is one step before standard deviation. We took variance, took the square root to get standard deviation. Well, we're not going to take the square root. We're just going to use variation. And the concept is this. We're going to create 2 estimates. And imagine if we had 2 estimates for variance from this distribution. If we had the estimate 1 and the estimate 2, and we did division with those, we get the number 1, right? Because they should be exactly the same. Whereas over here are 2 estimates of variation. One is going to come from the difference between each mean, which will be like the difference between each one of these. So if the variation is from a situation like this, then we're going to get some huge number, and we'll use that in the numerator. The second estimate for variation will come from each one of the individual distributions, which will be in the denominator. So when we get this situation, when we do the division, we'll get some big number. So the idea is 2 estimates of variation from a distribution like this, divide one by the other, we get about 1. From over here, we're going to get something much bigger than 1. And that will indicate that the means are not all the same. Now, guess what? We're going to use a different distribution. And I'm actually going to page down, page down. We're going to use something called the F distribution. Now the F distribution will be able to take our two estimates of variation, do our division, and that will give us some number. And we'll compare it, right? Somewhere between 1 and 2, or whatever the cutoff is using our hypothesis testing. Somewhere in here, that number will be just fine, which means it's close enough to 1 to say there's no significant difference. But at some point, we're going to have a cutoff, whether it's 3 or 4 or 5. And past that cutoff, we'll be able to say there is a significant difference between at least 2 of the distributions. Now I'm going to go page back up. 2. Now, this picture shows 4, like they're all totally different. But this analysis will show that just at least 1. We won't know exactly which ones, but we'll know there's at least 2 that are significantly different. Now, this is page 31. We were just on page 33. I want to go back to page 32. We're actually going to have MSTR, which is the mean square of treatments. That's going to be our one estimate of the variability between the samples. Then we're going to have mean square error. That's the estimate of variability within each sample. We'll do our division. Boop, boop. Too big, and we won't think that the means are all equal. Close to 1, it'll be reasonable to assume that the means are equal. Now, hypothesis testing with Anova, the null hypothesis is going to be mu sub 1 equals mu sub 2 equals mu sub 3 equals mu sub 4. And the alternative hypothesis will be not all population means are equal. But really what this means, if we reject the null hypothesis, we cannot conclude that all means are different, only that at least 2 population means are different. Now, this is page 32. I want to page down all the way to, let's say, 35. This isn't a screenshot of our Excel example. These are the answers that we'll get when we make our calculations. You can notice it's going to be calculation intensive. Page down. This is a page for you, like your cheat sheet, to know which formulas to use for which calculation. Page down to go to page 37. And this will be our built-in feature from the Data ribbon tab, where we'll do Anova single factor, and it will spit out our numerator, denominator, our F statistic, our p-value, our critical value. Now I want to page down 38. Here's some of the formulas from the book, page 39. This is the one that we're going to use. It's called mean square due to treatments. Remember, that's the populations. That'll be the actual variation between each one of our means. Again, they use treatments for population. That's the formula. We're going to do it over in Excel. That'll be the numerator. Page 39, I'm going to page down page 40. Our second estimate for variability, and this one will be within each sample. This will be the mean square due to error, MSE, and this will be our denominator. All right, that's a lot of stuff, so it's going to make more sense when we go over to Excel. And so I'm going to go over to Excel, and I'm on the sheet Anova long. Now I'm going to do the same example 3 ways. I'm going to do it the long way, and this long way will help us see the actual calculations for variation. Then we'll do it the more abbreviated way, and we'll use the sum product function like we did in earlier chapters when we were calculating standard deviation from frequency distributions. And then we'll see the automatic built-in way from the Data tab. All right, so here are method 1 to 4 and all of our numbers. The first thing we need to do is count. In this example, each one of the counts for each one of the treatments is the same. That's not always the case. So I'm going to use the count function. The count function simply counts numbers. Control-Enter, and then copy it over. X bar for each one of those equals average. Highlight, Control-Enter, and copy it over. Now, when we go to calculate variation, one of the calculations between the treatments will be the difference between the variation between these different means. Now, this is analysis of variance, so I'm going to calculate sample variance. And I'm going to use VAR and .S. These are samples. Now, this variation calculation right here is calculating the variation within this one sample, right? Control-Enter, and copy it over. That's the mean for method 1. There's the variance for method 1. There's the mean for method 2. There's the variance for method 2. Now, one of the keys to this calculation is that we have a bunch of numbers. Yes, they're broken into 1, 2, 3, 4 different methods for calculating a quad. But we do want to count all of them. And we want to calculate the grand overall mean. So simply use count. That counts numbers. And that'll give us 20. Now the grand overall mean equals, oh yeah, we just use average. There's a fancy formula in the textbook, but that's all we really have to do if we have all the individual numbers. Now, I'm going to hit Enter. 12.969. That's the overall mean for every single one of the methods. Notice that the mean for each different method is different than the grand overall mean. Now, if you're calculating grand overall mean and you have all the numbers, that's fine. But occasionally, you'll be given the actual x bar and the count, and you will not have all of the individual numbers. So the grand overall mean can certainly be calculated there, but we're going to do a weighted average. If you remember all the way back to Chapter 3, here's the number 5 times. Here's another number 5 times. 5 times, 5 times. So we can calculate the weighted average. And we use the sum product. Here's the 4 means. And we're going to multiply 1, 2, 3, 4, comma, times our second array, times 5. So in essence, it'll say 5 of those, 5 of those, 5 of those. And what does sum product do? It multiplies, whoop, whoop, each one of the elements in the 2 arrays, and then it adds. That's not quite what we want. That's the numerator for a weighted average. We then need to divide it by the sum of all of the counts. And that will give us exactly the same number as this. Again, if you are given just the sample x bars and the counts, that's how you'd have to do it. In all of our examples, we're given all of the individual numbers. Now we have to count our treatments because we're going to use that in part of our calculations. 1, 2, 3, 4. I'm going to use equals count because I want to count text, method 1 all the way to method 4. That'll give us 4. And Enter. Now the calculation for total variance, that's going to be one of the calculations we're going to have to do. Then we're going to do between the treatments, between these, and then we're going to do within each treatment. But let's do overall first. And here's the idea. Each one of these is an individual time. If we just had this was a big sample, well, what we would do to calculate variation, we would go ahead and calculate the average, subtract the grand overall from each one of these amounts, square it, and then add it up. That's variance. So watch this. I'm going to, in this cell right here, equals open parentheses, relative cell reference. Now I'm going to copy this formula down and over. So that relative cell reference down and over will get every one of the times, minus the grand overall mean. And that needs to be locked in all directions. So I hit F4, close parentheses. Caret 2. That's the essence of a variation calculation. The particular value minus the mean squared. Control Enter, and I can copy it down. And this is a 2-step process. I copy it down, let go, and then drag it over. I go to the last corner cell and hit F2, and I can see, sure enough, it got it exactly right. Now, notice sum of squares. Each one of these is a deviation, and then we square it. So when they say sum of squares, the squares is each one of these calculations. So that's where the phrase sum of squares come from. Alt equals, and I'm going to sum all the squares. And this is the total for the entire 4 methods. Now, one nice thing about calculating this is when we go and calculate our 2 estimates for variation, sum of the squares for treatments and sum of the squares for errors, that will be our target because these 2 estimates, SSTR and SSE, they better add up to exactly that. Another thing we're going to need for this calculation is degrees of freedom. And we defined degrees of freedom earlier in the class as total observations minus the number of samples. Well, what do we do here? Each one was an observation, each one of these. So there's 20 total. And how many samples did we take? We had one sample mean. So for degrees of freedom for this calculation, we have to say all of them minus how many samples? We only did one. One grand overall mean, so I subtract 1. And that gives us degrees of freedom. Now, interestingly enough, with these two items, we can get our sample variance for the entire sample here. So this is like a check number equals variation of the sample. And I simply highlight all of them. Notice it knows what to do. It's going to calculate the grand overall mean, calculate the deviation for each one of these, add up the deviations, and divide by n minus 1. So when I enter, that's the sample variation for all of them. And guess what? If we divide these two, here's the sum of all the deviation squared divided by n minus 1, and exactly the same thing. All right, so that's going to be our target for our sum of squares for our two calculations down here. Now we've got to talk about calculation variance between the treatments. Now here's the deal. That's a mean, that's a mean, that's a mean, and that's a mean. If we calculate the deviations for each one of these as compared to the grand overall mean, square them and sum them, that will get us to our sum of squares for treatments. So down here, I'm going to calculate the deviation squared for each one of our sample means. So you ready? Equals open parentheses, relative cell reference. Notice when I copy it over here, it'll move relatively, minus the grand overall mean, F4 to lock it, close parentheses, and caret 2. Control Enter, and copy it over. Now, one conceptual jump we're going to have to make is notice up here, we actually made a calculation, 20 different calculations. This is going to be much too small as our estimate. So because we only did 4 of them, we're actually going to have to multiply each one of these times the sample size for each one of these. So total deviations. So I'm going to take my actual individual deviation squared times the sample size. So I'll get 5 of those, 5 of those, 5 of those, 5 of those. And when it adds it up, it'll be parallel in size to this one up here. So I Control Enter and copy it over. Go to the last cell in F2. I'm just checking. Are the two relative cell references correct? Yes, they are. Now, sum of squares of treatments. Remember, treatment means population. That means the difference between each one of the methods. Alt equals, and I'm going to very carefully highlight these, and Enter. So 23, that's going to be part of the calculation in the numerator. Before we can get the actual numerator, we have to calculate degrees of freedom. Now we need to be careful here. When we made this calculation, notice the individual elements, there were only 4 of them, right? 4 total. And how many samples did we have? 1 grand overall mean. So the degrees of freedom equals, number of treatments k minus 1 sample. Now, this is the sum of square of the treatments. That's the degrees of freedom in order to calculate our estimate of variance between the treatments. That's the mean square of the treatments. We have to take our SSTR divided by degrees of freedom. So in this cell equals SSTR, sum of the squares of treatments, divided by our degrees of freedom. So when I hit Enter, there's our first estimate of our variation. Now we have to calculate estimate of variance within the treatments. That's called the mean square of the error. All right, now we're going to scroll down. And I'm going to try and scroll down just so we can see. And I'm going to try and fit this on the screen. I know this is kind of small, but here we go. Equals, open parentheses, the very first time in method 1 minus our actual mean. Notice we're going to calculate the variation within this method. F4 to lock it, close parentheses, caret 2. The deviation, we're going to square it. Control Enter, and copy it down. Now we're going to have to do that calculation for each one of these. So it equals method 2, that's the individual time, minus the actual mean. And I'm going to F4, close parentheses, and caret 2. Control Enter and copy it down. All right, and I'll let you do these last two. All right, so I did each one of these, and I'm checking up here. It's looking good. Now I simply need to add Alt equals, Control Enter, and copy it over. Now each one of these is the total deviation squared for each one of the methods. Now we need to add them up. Alt equals, and I'm going to add up just the bottom row, the total deviations, and Enter. Now I need to calculate the degrees of freedom, and we have to think, how many individual values did we have? Notice for the first method, we had 1, 2, 3, 4, 5. We had 1, 2, 3, 4, 5. So there's total 20 individual values. And how many samples did we have? Well, if we look right here, we had 1. And look right here, 2. Look right here. So each one of these means constitutes a sample. So our degrees of freedom, if it is observations minus samples, 20 total observations. And we subtract our 4 samples. So the degrees of freedom equals 16. Now we can come over here and calculate our estimate of variation within the treatments. Mean square of the error divided by our degrees of freedom. So equals sum of the squares of error divided by our 16, our degrees of freedom 16, and I get Enter. So there's our two estimates. If they were exactly the same when we divided them, we'd get 1. And here is our division. This is the kind of the drum roll, our F-test statistic. Mean square of the treatments divided by mean square of the error. So equals mean square of the treatments divided by mean square of the error, and 1.57. Remember what we said? If this number comes out close enough to 1, then we're going to say there's not a significant difference between the means. If it somehow passed our hurdle, then we'd have to say there's a significant difference. And where is that hurdle going to come from? It's going to come from the F distribution. Now we can calculate p-value, which is dist, or the critical value, which is inverse. So we're going to start with the F critical value. And luckily, when I type F dot, there's dist. And we're going to use the dist right because we're interested only on the upper end, and F dot inverse. Again, we're going to use right because we're interested on the upper end only. But these functions work the same as before. Dist will give us probability. Inverse will give us an actual value. Now, there's some notes over in the PDF on the page that talks about the F distribution. We put the probability, and because we're using the right, we give it the entire alpha probability. And I can see I haven't put that there yet. I'll have to put that in after. It's 0.05, comma, and then we have 2 degrees of freedom, treatments, and then error. So for the degrees of freedom, that's the first one. That's the treatment. So I click on the 3. Comma, and then the degrees of freedom 2, that's going to come down here. That's the error. And that's it. This F.INV.RT will give us our hurdle. Now it gives us a num error, so I'm going to come up here and put 0.05. There's our risk of rejecting the null even though it was true. So when I enter that, there's our hurdle, 3.238. And we can see our F-test statistic is nowhere near past our hurdle. So we are not going to reject the null and accept the alternative. It seems reasonable to assume that the means are equal. Now we can calculate our p-value. Remember, p-value is compared directly to our alpha risk equals F.DIST. And I'm going to use the right again because we're interested on the probability only on the upper end. All the probability past that test statistic, that'll be our x, which is F-test statistic, comma, degrees of freedom. That's the treatment, comma. And then our degrees of freedom, that's the error down here. That's the 16. Close parentheses. And my guess is we're going to get a pretty big probability. Control Enter. That is a lot of probability. So the probability of going out and getting a 1.57 F-test statistic or more is 23.5%. So because our p-value is much bigger than our alpha, we have strong evidence to suggest that the means are actually equal. The sampling difference between the average time for each one of the methods is not significant. Now, we did this the long way. We want to go over and look at a shorter way to do this. But before we click on Anova Short, I just want to remind ourselves over here, when we made our first calculation, notice that our formula actually looked at this whole rectangular range. And for every single one of them, we subtracted the grand overall mean and then squared them and then added. So instead of doing this whole table method over here, we can do all of this in a single cell. Let's go over here. And we've seen formulas similar to this earlier in the class using the sum product function. Now, I already went ahead and same example. I did count, average, the variance, grand overall count, the grand overall mean, and our total for our treatments. Now, let's go ahead and we're going to do SST, which is sum of the square total, and then SSTR for sum of the squares treatments, and then SSE, sum of the squares of errors, all with single cell formulas. Hey, let's remind ourselves of sum product. Sum product's amazing because we can make array calculations. That's why that argument's called array. And it will understand and add them for us. Now, if I highlight all of these cells, I just put all of these numbers from the cells inside this formula. And if I say I want to subtract this grand overall mean, Excel knows to take every single one of these numbers and subtract that grand overall mean. Now, we've done calculations like this before. For example, when we did standard deviation from a frequency distribution. Now, I'm going to put parentheses around this because I need to force that subtraction first, and then caret 2. Now, actually, why don't we do this? I'm going to highlight and hit the F9 key. You can see here it calculated every single one of the deviations. So there's 20 of them here, and if you count all those numbers there, there's 20 of them. Control Z. Now, once we get all 20, when I do a caret 2, it'll square all of those. And so if I F9, if you look at the number 0.1672 and then 1.2, if you go over on that other sheet, you'll see those were all the numbers in the cells. And we'll actually do that in just a second. Now, remember, our goal was to add up all those deviations. So then I simply hit Enter. And boom, there it is. Now, let's go back over here and notice that sure enough, 1.16, 1.12, every one of those numbers were calculated in our single cell formula. Now, that's pretty cool. Now, we can calculate our degrees of freedom. Remember, there was 20 total individual items, and we had one sample, so we subtract 1 to get our degrees of freedom. Now, let's come and do our sum of the squares of treatments. Now, how do we do the treatments variation? Remember, we took each one of the individual means and subtracted the grand overall mean. However, we also had to bump it up to the same scale of this, so we multiplied each one of those numbers times 5. No problem. Instead of doing it in our 2 steps right there and multiplying it by the 5s, we can do it all in one cell to get that number. Sum product comes to our rescue in 2 ways. It will understand our array calculation when I say, hey, give me all the means, and I'm going to subtract the grand overall mean, close parentheses, and caret 2. Now, remember, when we did it on that other sheet, we did 1, 2, 3, 4 numbers, subtract, whoops, I got the wrong number there. We did 1, 2, 3, 4 numbers, subtracted that. If I were to highlight this and hit the F9 key to evaluate, you could see sure enough, I got the 1, 2, 3, 4 exact numbers we got on the other sheet, but inside our formula. And then we simply square it. Those are the numbers we got, that 0.059, 0.74, Control Z. Now, what did we do? We then multiplied each one of those numbers, and that's where sum product comes in a second time. We can take the first array, those 4 numbers, comma, and the second array, those four numbers. It'll totally multiply each one of the four numbers from in there times boom, 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 boom. And then it will add it. Remember, the meaning of sum product is that it multiplies the two arrays, array 1, array 2, and then it adds them. That's the sum part. So when I enter, there it is. I don't know about you, but I certainly like doing that formula there more than doing this. We did it over here longhand just to see the meaning and remind ourselves how we did deviations and deviations squared earlier in the class. But once you get the hang of it and you're using formulas, that's the way to go. In your PDF handouts, the sheet with all the formulas come from this sheet, because this is the way you should do it if you're doing formulas. Now remember, here we had 1, 2, 3, 4 individual items, and we subtracted one sample mean. So here the degrees of freedom are 4 total items minus 1 sample mean. Now we can calculate our mean squared of the treatments. So you ready? Equals SSTR divided by our degrees of freedom. And boom, there it is. So in 1, 2, 3 cells, we made our necessary calculation as opposed to over here doing it a bunch of cells. All right, and now we go over to sum of the squares for the error. Now here's what we want to do here. And we can even go look on the long sheet. Oh yeah, we had to actually calculate the deviation for each one of these. Take each one of these numbers and subtract the corresponding mean. Now notice I'm over here, and I'm going to get this whole column minus that. So if I were looking at this one at a time, notice that each one of the blue ones in this column is subtracting the same number in that orange cell. So we can actually make a similar array calculation. We can take the entire 20 amounts as a range and subtract the 4 means. And if we do that, we'll get exactly all of these numbers here. So that 0.02, that 3.84, etc. So I can come over here, and for SSE, sum of the squares of errors equals sum product. Open parentheses, and watch this. I'm simply going to take all of those and subtract these. Now, when you do an array operation like this, notice it's a rectangle range subtracting a single row of items. It knows to take every one of those and subtract that, every one of those and subtract that. Now we need to square that. And if we highlight that, or simply click on this array 1 and hit F9, there's the actual numbers, that 0.02, that 3.84 that we saw just a second ago, all inside of a single cell. Totally amazing. Now we simply close off, and when we hit enter, you've got to be kidding me. There's that 7869, same exact number we got over here. So we can do it the long way, or we can simply do it our short way with sum product. Now we want to calculate our degrees of freedom. We had all 20 items. So I'm going to take that 20. And we had 1, 2, 3, 4 sample means. So we're going to subtract 4. And there's our degrees of freedom, 16. Now there's an actual another way we could do this if we calculated the variance. Now remember, that calculation took all of the deviations, squared them, added them up, and actually divided, because it's a sample, divided that by 5 minus 1. So we could actually calculate this by taking all of these and multiplying them not by 5, but by 4. Because remember, the step before calculating variance is to take the sum of the squares and divide by the degrees of freedom. So really what we're going to do here is take this. This has already been divided by the degrees of freedom. So we're going to take this and undivide it by multiplying it by 4, 4, 4, 4. So you ready? Equals sum product. I simply take the variance. Remember, this is within the variance within each method or treatment, comma, and then I'm going to take each one of those, and I need to subtract 1 from each one. So I do another array calculation. And you could prove that to yourself. F9, and you see it gives us 4, 4, 4, 4. So it took the 1 and subtracted from each one of the 5s. Control Z. close parentheses, and enter. That's the exact same thing. A nice way to have our check figure. Now we can check this one. Remember, the overall total variance better add up to exactly SSTR, sum of the squares between the treatments, plus the sum of the squares of our error. And boom, so we have a check for each one of those. Now our mean square error equals sum of the square of error divided by our degrees of freedom, and boom, there it is. Now we can calculate our F.test statistics. That equals the mean square of treatments divided by the mean square of the error, and enter. Wow, there is our F statistic. If we calculate we're going to calculate our critical value, but this time I'm going to put the alpha in first. So equals F dot inverse, because we're calculating the value, and we're using the right because we want only the amount on the upper end. So I'm going to give it just the probability on the upper end. Remember, degrees of freedom, the first one is the treatments, comma, the degrees of freedom for the second, that one is the error. And there is our same critical value. There's no way this is not even close to pass our critical value. So we fail to reject the null hypothesis. And if we do our p-value, it's the same thing. F dot, and we're using DIST because we want a probability, and we're using right because we're on the upper end. It's going to give me the probability of getting 1.5 F-test statistic or more, comma, degrees of freedom. We take the treatment, comma, and our error. Control Enter. There's that probability of 0.235. So because our F calculated test statistic is not past our F critical, we fail to reject the null hypothesis. It seems reasonable to assume that the population means are the same. There is not, even though there's sampling difference up here between each one of our times for each one of our manufacturing methods, the differences are not significant. Now, we got to look at one last way of doing the Anova. I'm going to come over here to the data analysis. Oh, you got to be kidding me. Notice I have our null hypothesis and alternative here. And all I need is the actual numbers. You're not going to believe this. Data analysis. And scroll up. There it is. Anova. So right at the top, Anova single factor. And when I click OK, it'll ask me for the input range. Notice it's only one. Be sure and have your labels at the top and all your numbers. It'll know column, column, column. Each one of those is a different treatment. It's in columns. Labels are definitely in the first row. Our alpha is 0.05. Our output range, I'll put it right in A16. And you got to be kidding me. Look at that. There are our averages for each one. There are our variances. There's our sum of the squares. Now in the Anova table in Excel, between means treatments. Between the treatments, and the within means the error within each of the individual treatments. And so there's our 23, there's our 78, there's our 101, right? There's the degrees of freedom, there's the total. There's our mean squared for the treatment, mean square for the error, our F-test statistic, probability of getting that test statistic or more. It's huge. And there's our F critical value. So in all three cases, of course, we got the same numbers, the same answers. Because our p-value is larger than our alpha, we fail to reject the null hypothesis. It seems reasonable to assume that the population means are the same. All right, in this video, we talked about completely randomized design and Anova to determine whether the means for various populations or treatments are the same. We saw the built-in data analysis Anova single factor feature. We also saw how to do it with formulas, the short method. We saw how to do it. Formulas, the long method, but really if you're going to do formulas, you want to do these short methods. All right, that's it for Chapter 10. Next chapter, chapter 11, we'll talk about comparing two population proportions. All right, we'll see you next video.